Okay, lecture 16 of algebra, and I'm going to start by going over the midterm. Let's see if I can pull this over a little bit. So problem 1 was to show every positive integer can be written as a product of prime numbers. So of course, n equal 1 is a product of 0 prime numbers. That's an empty product. N equal 2 is a product of 1 prime number, namely itself. So the proof will be by induction on n. So suppose the statement is true for all integers n less than or equal to some number capital N. We want to prove this for n plus 1. So there are two cases. In the first case, n plus 1 is a prime, and we're done. In the second case, n plus 1 is composite, which means n plus 1 factors into a product of two numbers, n1 and n2, with n1 and n2 both numbers between 2 and n. That is, neither of these is equal to 1. They're both at least 2, and they're both strictly smaller than n plus 1. So by the induction hypothesis, n1 less than or equal to n, which means less than n plus 1, means n1 is a product of primes. Is there a question? And n2 less than or equal to capital N, which means strictly less than n plus 1, means n2 is some other product of primes. And so n plus 1, which is n1 times n2, is P1 up to Pk, Q1 up to Ql. It's a product of primes. And we're done. Any questions about that? And the second part was just to factor a number, which everyone I think could do. Okay, no questions? Problem 2. Find the greatest common divisor of 245 and 567 by using the Euclidean algorithm. So if you take 567 and divide it by 245, let's see, that's 590, and that leaves a remainder of 77. If you take 245 and divide it by 77, that goes in 3 times. This is 231 and leaves a remainder of 14. If you take 77 and divide it by 14, that goes in 5 times and leaves a remainder of 7. And if you take 14 and divide it by 7, that goes in 2 times and leaves a remainder of 0. So the GCD of 245 and 567 is 7. And then to write 7 as a linear combination of 245 and 567, we work backwards. According to this, 7 is 77 minus 5 times 14. According to this, 14 is 245 minus 3 times 77. So if you collect what you have here, you have 1 times 77 minus 5 times minus 3 is 15 times 77. So you have 16 times 77 minus 5 times 245. And from this, 77 is this minus this. 77 is 567 minus 2 times 245 minus 5 times 245. So I have 16 times 567 minus 32 minus 5 minus 37 times 245. So this is 7 as a linear combination with integer coefficients of 567 and 245 obtained directly from the Euclidean algorithm. Okay. Any questions about this? Problem 3 is to prove 2 identities in set theory. So we want to prove that the complement of S union T is the complement of S intersected with the complement of T. So X is in S union T complement if and only if X is not in S union T. That's what it means to be in the complement of a set. And X is not in the union if and only if X is not in S and X is not in T. X not in S means X is in S complement. X not in T means X is in T complement. And X is in this set and this set if and only if X is in the intersection of the 2 sets. Some people thought this problem, and even the next part of this problem, had something to do with the distributive laws for sets and with respect to union and intersection, but it does not. Okay. Any question about this part? Part B is to prove that the complement of a set is equal to the set. So let's see, what does that mean? So X is in the complement of S if and only if X is not in S complement. Right? It's like here we have our universe, here's S, and this is the complement of S. So every element is either in S or the complement of S. If X is not in the complement of S, that means X is in S. And that's the whole proof. Question? So problem 4 is to prove that if A is congruent, A1 is congruent to A2 mod M, and B1 is congruent to B2 mod M, then A1, A2 is congruent to B1, B2 mod M. So the proof is as follows. If A1 is congruent to A2 mod M, that means A1 is A2 plus some multiple of M. And if B1 is congruent to B2 mod M, that means B1 is B2 plus some multiple of M. If you put these together, A1 times A2 is A2 plus MX times B2 plus MY. You multiply A2, B2, you get then M times A2Y, M times B2X, and M times MXY. So A1, A2 is A2, B2 plus a multiple of M. So A1, A2 is congruent to A1 to, oops, sorry. This should have been A1, B1. So A1 is A2 plus MX, and B2 is B2 plus MY. So this is A2, B2 plus M, A2Y plus M, B2X plus MXY. So that part is all correct. So A1, B1 is congruent to A2, B2 mod M. That's the proof. All right. Any questions about this? Problem 5 is to solve two sets of congruence equations. In part A, we want to find all solutions of 2x congruent to 17 mod 7. So there are many ways you can do that. I mean, you could just plug in. There are only 6 possible congruence classes mod 7. You could plug in x equals 0, 1, 2, 3, 4 until you find a solution. 5, 6 until you find a solution. You could also say 17 is congruent to 3 mod 7. So this is the same as 2x congruent to 3 mod 7. You could also observe, if you like, that 4 times 2 is 8 is congruent to 1 mod 7. So if I multiply this congruence by 4, I get 4 times 2x is 4 times 3, which is 12, which is 5 mod 7. And 4 times 2 is the same as 1 mod 7. So we get, this is the answer, x congruent to 5 mod 7. I mean, there are lots of different ways to solve the congruence, but there's only one answer, and this is it. And you can check. 2 times 5 is 10, and 10 minus 17 is minus 7. It's minus 1 times 7. So 2 times 5 is congruent to 17 mod 7. It checks. Okay. Any questions about that? Part B, we want to solve a system of congruences, x congruent to 2 mod 9, and x congruent to 3 mod 7. That is, we want to find all numbers x that satisfy these two congruences. So this first congruence says that x is 2 plus some multiple of y. So x is an integer of the form plus x plus 9y. And this has to be congruent to 3 mod 7, which is the same as 9y congruent to 3 mod 7. Of course, 9 is congruent to 2. So this is the same as 2y congruent to 3 mod 7. If I multiply by 4, 8y is congruent to 8 times 3 is 24. 8 is 1, so y is congruent to 24 mod 7, which is the same as 3 mod 7. Oops. Let me just double check what I did here. X is 2 plus 9y, so that has to be congruent to 3 mod 7. So 2y, oops, sorry, 3 minus 2 is 1. Should be able to subtract. Right. 2 plus 9y congruent to 3 is the same as 9y congruent to 1, and 9 is the same as 2. So if I multiply by 4, I get 8y, which is the same as 1y mod 7, is congruent to 4. Multiply by 4 mod 7. Which means y is an integer of the form 4 plus 7z. So x, which is 2 plus 9y, is 2 plus 9 times 4 plus 7z. This is 36. So x is 36 plus 9, 7 is 63 plus 63z. So x is every integer of this form, or in other words, the solutions are all x congruent to 36 mod 63. Oops, I'm sorry. 36 plus 2 is 38. X is congruent to 38 mod 63. That's the right answer. Right. Any questions about problem 5? Well, after problem 5 must come problem 6. So in problem 6, we have the permutation sigma in S7. So permutation of the integers 1 through 7. 1 goes to 5, 2 goes to 4, 3 goes to 6, 4 goes to 7, 5 goes to 3, 6 goes to 1, and 7 goes to 2. And I want to write this as a product of disjoint cycles and also as a product of transpositions. So let's just follow the trajectory of, you can start anywhere. I'll start with 1, but I don't have to start with 1. 1 goes to 5. 5 goes to 3. 3 goes to 6. 6 goes back to 1. So this is a 4 cycle. Let's see, what number is not here? 2 is not there. 2 goes to 4. 4 goes to 7. 7 goes back to 2. So here I have sigma as the product of 2 disjoint cycles. And if I want to write this as a product of transpositions, I can do this in infinitely many ways. I can write 1536 is 155336, and 247 is 2447. If we want to double check that this is correct, let's see, 1 goes to 5, 2 goes to 4, 4 goes to 7, 3 goes to 5, goes to 1. Oops, sorry, 3 goes to 6, 4 goes to 7, 5 goes to 3, 6 goes to 3, goes to 5, goes to 1, so 6 goes to 1, 7 goes to 2. So this is good. What is sigma squared? Well, it's this. It's sigma times sigma, 1, 2, 3, 4, 5, 6, 7, 5, 4, 6, 7, 3, 1, 2. And I'm multiplying this by itself, 1, 2, 3, 4, 5, 6, 7. I don't have to write all this out. I can do some of this in my head if I want, but I'm being very specific here. So when I compose these two functions, you always have to remember a permutation is a function. What happens to the number 1? 1 goes to 5 and 5 goes to 3. 2 goes to 4 and 4 goes to 7. 3 goes to 6 and 6 goes to 1. 4 goes to 7 and 7 goes to 2. 5 goes to 3 and 3 goes to 6. 6 goes to 1 and 1 goes to 5. 7 goes to 2 and 2 goes to 4. So in standard form, this is sigma squared. And if I want to write this as a product of disjoint cycles, let's see, 1 goes to 3, 3 goes back to 1. 2 goes to 7, 7 goes to 4, 4 goes back to 2. 5 goes to 6, 6 goes back to 5. So sigma squared is a product of a 2-cycle, a 3-cycle, and a 2-cycle. There's 2 transpositions and a 3-cycle. Okay. What is sigma inverse? Sigma sends 6 to 1, so the inverse sends 1 back to 6. Sigma sends 7 to 2, so the inverse sends 2 back to 7. Sigma sends 5 to 3, so the inverse sends 3 back to 5. 2 goes to 4, so 4 goes back to 2. 1 goes to 5, so 5 goes back to 1. 3 goes to 6, so the inverse sends 6 back to 3. 4 goes to 7, so the inverse sends 7 to 4. So in a standard form, this is sigma inverse. And if I write this as a product of disjoint cycles, let's see, 1 goes to 6, 6 goes to 3, 3 goes to 5, 5 goes back to 1. And 2 goes to 7, 7 goes to 4, 4 goes back to 2. So that's sigma inverse as a product of disjoint cycles. Okay. Any questions so far? So then we go to problem 7. So we have 2 matrices, S, which is 0, -1, 1, 0, and T, which is 1, 1, 0, 1. First, we have to do some matrix multiplications. What is S squared? So I have 0, -1, 1, 0, composed of 0, -1, 1, 0. If I do my matrix multiplication, row into column, I get -1, 0, 0, -1. What is S inverse? This matrix has determinant 1. So the formula for the inverse says interchange the diagonal elements. Well, 0, 0, interchange still is 0, 0, and just change the signs of the opposite diagonal elements. So this becomes 1, -1. Oops, that's true, but I was asked to find T inverse. So T inverse, again, this is determinant 1. Interchange these. This is still 1, 1. Change the signs of these, 0, -1. So that's T inverse. And S times T, 0, -1, 1, 0 times 1, 1, 0, 1. This is equal to 0, -1, 1, 1. So this, and this are the answers to the questions in part A. In part B, we want to compute by induction t to the n for all non-negative integers n. So of course, and we want to show that t to the n, so show t to the n is the matrix 1, n, 0, 1. So for n equals 0, 2 to the 0, and a matrix raised to the 0th power, a square matrix, is the identity 1, 0, 0, 1. So you have n equals 0 in this upper right-hand corner. T to the first power is just t, 1, 1, 0, 1. So here we have a 1. Let's just check t squared. T squared is 1, 1, 0, 1 times 1, 1, 0, 1. If you multiply it out, you get 1, 0, 2, 1. And here you have a 2 in the upper right-hand corner. So the proof is by induction on n. Suppose t to the n is 1, n, 0, 1. Then t to the n plus 1, that means t times t to the n. That's 1, 1, 0, 1, 1, n, 0, 1. When you multiply, you get 1, 0, n plus 1, 1. And you have an n plus 1 here. So the result follows by induction, and we're done. And part C, if you take 2 to the m times t to the n, so now we know that t to the m is 1m, 0, 1, and t to the n is 1n, 0, 1. And when we multiply, we get 1, 0, m plus n, 1, which is t to the m plus n, which is what we wanted to prove. So it's all, everything comes down to just matrix multiplication. Problem number 8 is to prove 7z is a subgroup of the additive group of integers z. So in general, in an additive group G, a subset H is a subgroup if 0 is in H, A and B in H implies A plus B is in H, and A in H implies minus A is in H. So I'm just going to check these three properties for the case when the group is the integers and H is 7z, that is all the multiples of 7. So first of all, 0 is 7 times 0 is in 7z. And if A and B are in 7z, then A is equal to 7 times some number A prime, and B is 7 times some number B prime. So A plus B is 7A prime plus 7B prime, which is 7 times A prime plus B prime. This is 7 times an integer. So that's in 7z. And if A equals 7A prime, then minus A is minus 7A prime, which is the same as 7 times minus A prime. Again, this is an integer multiple of 7. So this is in 7z. So all three properties are satisfied, and we have a subgroup. Again, there are other arguments that you can give to prove this that are equally valid. This is just a simple, straightforward way to do it. So the last problem is problem 9. We have a group G with identity element denoted by E and elements X, Y, Z, and G. We want to prove the inverse of X, Y, Z is Z inverse, Y inverse, X inverse. So the actual proof is straightforward enough. If I take X, Y, Z, and I multiply it by Z inverse, Y inverse, X inverse, by associativity, this is the same as XY times ZZ inverse times Y inverse, X inverse. And this is the identity. So this is XY times Y inverse, X inverse. And this is the identity. So this is XX inverse, which is E. And that's all we need to do for the proof. In part B, we have the commutator, what is called the commutator of the elements X and Y. This is defined to be X inverse, Y inverse, XY. If that's equal to E, then if I multiply both sides by X, I get X times X inverse, Y inverse, XY is X times E. But here the X and the X inverse cancel. So this is Y inverse XY equals X. And if I multiply both sides again on the left by Y, I get Y times Y inverse XY equals Y times X. But this is the same as Y inverse times XY, and Y inverse is the identity. So this is XY. So XY equals YX. And that's the whole proof. Any questions about anything on the exam? We'll have another midterm, the second midterm, sometime first or second week of May, so 5 or 6 weeks from now. Okay. Then we will start something new. Or not exactly new, but continuation of what we were doing before the midterm, where we were looking at a group, a subgroup, and a certain relation on the group. So let's take a look at all that. So much for this. Up to page 9 for these notes. So this is going to be about groups, subgroups, cosets, and what are called quotient groups, also sometimes called factor groups. So we have a group G, a subgroup H, and a relation, I'll call it squiggle, on G, defined as follows. For all elements X and Y in G, we say that X is related to Y. So this squiggle just means related if X inverse Y is in H. So X doesn't have to be in H and Y doesn't have to be in H, but they're related if X inverse Y is in H. And I showed, this is a week and a half ago now, the following properties of this relation. First, it's reflective. For all X in the group, X times X inverse times X is the identity, is in H, because the subgroup H always contains the identity, which means X is related to itself. That's what reflexive means. A property, a relation is reflexive if everything is related to itself. Second, this relation is what we call symmetric. If X is related to Y, then X inverse Y is in H. But H is closed under the operation of taking inverses. So X inverse Y inverse is in H. But the inverse of X inverse Y is Y inverse X. And if Y inverse X is in H, then Y is related to X. So X related to Y implies Y is related to X. So that's a symmetry property. That's what we call symmetric. And third, this relation is transitive. If X is related to Y and Y is related to Z, X inverse Y, X related to Y means X inverse Y is in H. Y related to Z means Y inverse Z is in H. And H is closed under multiplication. So X inverse Y times Y inverse Z is in H. But if I look at X inverse Y times Y inverse Z, Y inverse, that's the identity, that cancels. That says X inverse Z is in H. So X is related to Z. So that's what transitive means. If X is related to Y and Y is related to Z, then X is related to Z. So a property that has a relation that has the properties of being reflexive, symmetric, and transitive is called an equivalence relation, as we've discussed several times already. And whenever you have an equivalence relation, you have the equivalence classes. So what does an equivalence class look like? So an equivalence class in a equivalence relation squiggle, or let's say the equivalence class of X is the set of all Y such that X is related to Y. So if you have in general a set, in this case it's a group, you take an element X and the equivalence class is all Y such that X is related to Y. This means the set of all Y in the group, such that X inverse Y is in H. This means the set of all Y in G, such that X inverse Y is equal to H for some H in the subgroup capital H, which is the set of all Y. Just multiply through by H, bring this to the other side. Y equals XH for some H in H. And our notation for this is like X times capital H. X times capital H means all elements of the group that are X times an element of H. So the equivalence class of X in a group G with respect to a subgroup H is you take all the elements of H and you multiply them on the left by X. And this is called a left coset of H. It's H, all the elements of H multiplied on the left by this fixed element X. So that's the definition of left coset. And in an additive group, the relation squiggle is X is related to Y if Y minus an additive abelian group. If Y minus X is in the subgroup. And the equivalence class of X is the set of all Y such that Y minus X is in H. This means the set of all Y such that Y minus X is equal to some element little h for some H in the subgroup. This means the set of all Y such that Y is equal to X plus H for H in the subgroup. And we denote this, we just use, it's the same as the left coset here, except instead of a times sign, we use a plus sign, X plus H. So in an additive abelian group, we denote the equivalence classes of the left cosets by X plus H, because we're not multiplying, we're adding. So what's an example? Well, let's start with the additive case. Suppose I let G equal Z and H equal, how about 7Z, which is the subgroup we just proved in the midterm, all multiples of 7. So we say that, what is the equivalence class of an integer x? So that x be an integer, x plus h, or x plus 7z, this is all integers of the form, here, let me call this a instead, a plus h, all integers of the form a plus 7x, where x runs through all the integers. What is this? This is the congruence class of A in Z mod 7Z. Right? This is the congruence class of A modulo 7. 7Z itself, this is all numbers of the form 7x. You could think of this as 0 plus 7x. So this is 0 plus 7z, the equivalence class of 0, or the congruence class of 0. We don't usually write down the 0 here, right? So 7z is the congruence class of 0. 1 plus 7z is the congruence class of 1. What is it? 1, 8, 15, 22, minus 6, minus 13. Minus 20 and so forth, right? Congruence class of 1. So this notion of a left coset is familiar to you in the instance of congruence classes mod M. So the congruence class A plus MZ is the left coset of A with respect to the subgroup H equal MZ in the larger group G equal to Z. What about a multiplicative example? Well, we don't know too many non-abelian groups, but a fundamental example for us is S3. So let's look at that example. So S3 is a group with just 6 elements. And let's see what we can do with it. So suppose we take the group S3, and I want to find a subgroup. So that's my group. And I take the subgroup H that consists of the following 3 permutations: the identity, the cycle 1, 2, 3, and the cycle 1, 3, 2. So if I let sigma be 1, 2, 3, the cycle, sigma squared is 1, 3, 2. Sigma cubed, which is sigma times sigma squared, this sends 1 to 3 to 1, 3 to 2 to 3, 2 to 1 to 2. Sigma cubed is the identity, which means sigma inverse is sigma squared. So this is a subgroup with 3 elements. Suppose I take tau to be the transposition 1, 2. I want to compute the left coset tau h. So this is tau times this set of E, sigma, and sigma squared, right? This is E, sigma, sigma squared. So I multiply each of these permutations on the left by tau. I get tau times the identity, which is tau, tau sigma, and tau sigma squared. What are these? Well, this is tau. What is tau sigma? This is 1, 2 times 1, 2, 3. So this is the 3 cycle followed by this 2 cycle. This sends 1 to 2, and 2 goes back to 1. This sends 2 to 3 to 3. 3 goes to 1, goes to 2. So this is just the transposition 2, 3. What is tau sigma squared? That's 1, 2. Sigma squared is 1, 3, 2. So this sends 1 to 3. 3 to 2 goes back to 1. 2 goes to 1, goes to 2. So that's just 1, 3. So tau h, when I compute this coset, it's actually all 3 transpositions. 1, 2, 2, 3, and 1, 3. And in fact, what is the group S3? It has 6 elements. It has E, sigma, and sigma squared, and it has these 3 transpositions. 1, 2, 1, 3, 2, 3. So if I think of the group S3, here I have this subgroup H, and there are 3 elements in it, and the other 3 elements in the group are in tau H. So S3 is partitioned into the subgroup H and a single coset. So these calculations are extremely important, and they can be hard to follow when I'm just doing it in class. But it's important to go through these all very carefully at home and understand step by step what's going on. So an exercise you should do is, suppose I let tau be the transposition 2, 3. I'll call that tau 1. Compute the left coset tau 1h. And let tau 2 be the transposition 1, 3. Compute the left coset tau 2h. Not now, but these are things you should be able to do and that you have to learn how to do. Any questions about this? Well, since we're working with S3, let's look at another example. Suppose I take G to be S3. Suppose I'll call tau 3 to be the transposition 1, 2. So this is order 2. Tau 3 squared is the identity. And suppose we let H be the identity in tau 3. So this is a subgroup of S3. Compute the left cosets. So remember, S3 has 6 elements. E, sigma, sigma squared. This is the 3 cycle. And these 3 transpositions. Again, I'll remind you, sigma is 1, 2, 3. Sigma squared is 1, 3, 2, which is sigma inverse. Tau 1 is 2, 3. Tau 2 is 1, 3. Tau 3 is 1, 2. So these are the 6 elements of S3. So there's going to be 6 left cosets we can calculate. What is the left coset with the identity? That just means take each element of H and multiply it on the left by E. So I get E times E and E times tau 3. But the identity times the identity is the identity, and E tau 3 is tau 3. So EH is just H. What is tau 3 times H? So that's, I multiply everything on the left by tau 3, I get tau 3 times the identity, and tau 3 times tau 3. This is tau 3, and this is tau 3 squared. But tau 3, each of these transpositions, if you square it, you get the identity. So this is tau 3e. In a set, the order you write down the elements in does not matter. So tau 3e is the same set as E tau 3. So tau 3h is H. So these 2 cosets are the same as H. What about tau 1h? So that's going to be tau 1 times the identity, tau 1 times tau 3. Tau 1 times the identity is tau 1. What is tau 1, tau 3? Tau 1 is 2, 3. Tau 3 is 1, 2. What is this permutation? This sends 1 to 2 and 2 to 3. So 1 goes to 3. 3 goes to 3 goes to 2. 2 goes to back to 1. So this is tau 1 and 1, 3, 2, which is sigma squared. So the coset tau 1h is tau sigma squared, tau 1 sigma squared. What is tau 2h? That's tau 2 times the identity, tau 2, tau 3. Tau 2 times the identity is tau 2. What is tau 2, tau 3? That's 1, 3, 1, 2. This sends 1 to 2, 2 to 1 to 3, 3 to 3 back to 1. That's sigma. So tau 2h is tau 2 sigma. That's 4 of the cosets. Let's compute the other 2. What is sigma h? So that's sigma times the identity and sigma times tau 3. Sigma times the identity is sigma. What is sigma tau 3? That's 1, 2, 3 times tau 3, which is 1, 2. This sends 1 to 2, 2 to 3. So 1 goes to 3. 3 goes to 3, goes back to 1. 2 goes to 1, goes to 2. So sigma tau 3 is 1, 3, which is tau 2. So I get sigma and tau 2. And finally, what is sigma squared h? That's sigma squared e, sigma squared tau 3. Sigma squared times the identity is sigma squared. What is sigma squared tau 3? That's 1, 3, 2 times 1, 2. This is 1 goes to 2, goes back to 1. It doesn't move. 2 goes to 1, goes to 3. 3 goes to 2. So sigma squared tau 3 is the transposition tau 3, which is tau 1. So this is sigma squared tau 1. So these are the 6 left cosets of H. Of course, they're not all different. This is H and this is H. Tau 1 sigma squared. Here's tau 1 sigma squared. These two are equal. Tau 2 and sigma, these two are equal, and these two are equal. So there are 3 distinct left cosets of H in the group S3. And you'll notice the cardinality of S3 is 6. The cardinality of the subgroup H is 2. 6 over 2 is 3. So this is an example of what is called Lagrange's theorem, which says in a finite group, the number of cosets of a subgroup H is the order of the group divided by the order of H. And I proved that in the last substantive lecture, but I'm going to prove it again right now. So in a finite group G, the number of left cosets of G, which is called the index of H in the group G, it's denoted by G colon H in square brackets. That's the number of elements in G divided by the number of elements in H. So this is very important, and it deserves a star. And this statement is due to a French mathematician in the 19th century called Lagrange. And this is Lagrange's theorem.
Professor, you said G colon H?
Yeah, that's just a notation. We also write G mod H. This is the set of left cosets of H in G. So the order of this set, the number of elements in this set is the index of H and G. This is just, both of these are notations that are used all the time. Still the order of G divided by the order of H. So this is the number of left cosets. G mod H is the set of left cosets. So when you put absolute value signs around it, that means the number of elements in this set, which means the number of left cosets. But this is just a little bit more notation for the same thing. So how do we prove this theorem? So we're going to show all left cosets have the same number of elements. So let X be an element of the group. So the left coset XH is everything of the form X times little h for all H and H. So I can define a function f from the subgroup H to the left coset XH by f of H equals XH. So this function is 1-to-1 because f of H1 equals f of H2 if and only if H1x equals H2x, multiply on the right by x inverse if and only if H1 equals H2. So this function is 1-to-1 and onto f of H equals XH. Take any element in this left coset, XH is equal to f of H. F of H is just take H and multiply it. That's this definition. So this is onto.
Professor, do you mind just reading the last few sentences right there? So I guess
Well,
starting at
define a
define function.
Define a function f from H to the left coset XH by f of the element H is equal to x times H. So I'm defining a function from this set to this set. And if I take elements H1 and H2 in H, if f of H1 equals f of H2, that means H1x equals H2x. And this is a group. I can cancel the x. So H1 equals H2. So f of H1 equals f of H2 if and only if H1 equals H2. That's the definition of 1-to-1. This function is 1-to-1. And it's onto, because if I take any element XH in this coset, f of H equals XH. So something gets mapped onto XH by the function f. So it's onto. And the definition of two sets having the same number of elements is there's a function from one set to the other that's 1-to-1 and onto. So we're done. We just did it. So all left cosets have the same number of elements. And what else can we say about the left cosets? Every element X and G belongs to some left coset of H. Namely, X is in the left coset X times H, because X times E is in XH. So every element belongs to some left coset. And I can also say that the distinct left cosets of H and G are pairwise disjoint. This means that if XH intersect YH is not the empty set, then XH equals YH. So here's my group G. Here I have a coset XH. Here I have a coset YH. If there's some element in both of them, the two sets are equal. Right? Why is that? So here's the proof of this statement. Let Z be in XH, intersect YH. Then Z is equal to X times H for some H and H. I call it H1 for some H1 and H. And Z is equal to XH2 for some H2 and H. So therefore, sorry, Z equals YH2. So if Z is in XH, Z is X times H1 for some H1. If Z is in YH, then Z is YH2 for some H2. So XH1 equals YH2. Or another way of saying this is that Y is equal to X H1 H2 inverse. Suppose I let H1 H2 inverse, I'll just call it H. So this is y is equal to, I'll call it H3, XH3. So for all H in H, YH is XH3 times H. This is an element of H. H is a subgroup, it's closed under multiplication. This is in XH. So this means that every multiple of Y on the left by an element of H is in this left coset, which means YH is contained in XH. The set of all these YHs, that's the whole left coset, is contained in XH. And this is a symmetric argument. You can just repeat it interchanging X and Y. So I'll just say by symmetry, XH is contained in YH. So if you have two sets and each is contained in the other, then XH equals YH. So if two cosets have even one element in common, then they're exactly the same. So what this tells us is that the left cosets XH partition the group G. So let G mod H, this is the set of left cosets. So suppose, let's say K is the index of H and G, the number of left cosets. So the set of left cosets, you have X1H, X2H, X3H, up to X sub KH. So these sets are non-empty and pairwise disjoint. So if this is the group G, it's partitioned into these cosets, X1H, X2H, X3H, and so forth, up to X sub KH. So G is the union of these cosets, which have no elements in common. So the number of elements in G is the sum, I goes from 1 up to K of X sub IH. Right, again, K is the index of H and G, it's the number of left cosets. But all left cosets have the same number of elements. XIH, the cardinality of that is just the same as the cardinality of H. So this is the sum, I goes from 1 up to K, cardinality of H, which is, I'm just adding cardinality of H to itself K times. That's K times the cardinality of H. So K is the order of G divided by the order of H. That's what I wanted to prove. K is the index. So that's the end of the proof. Right. Very important proof. You really need to spend as many hours as is necessary working through the details and understanding everything line by line. So for example, if we take S4, permutations of 1, 2, 3, and 4, the order of S4 is 4 factorial. 1 times 2 times 3 times 4, which is 24. If I take sigma to be the cycle 1, 2, 3, 4, and let H be the cyclic subgroup generated by sigma, so that's the identity sigma, sigma squared, and sigma cubed, the order of H is 4. So if I want to know what is the index of H in the group S4, it's the order of S4 over the order of H. That's 24 over 4, that's 6. So if I start to calculate the left cosets of this subgroup in the group S4, I'll end up with 6 left cosets. Exactly. Right. Any questions about this? This is all very fundamental group theory. You'll find it in the book, and you'll find it, I think, better explained in the notes I put on Blackboard. But these are fundamental notions. Now, some groups are special. So remember, a left coset of H and G is something that looks like A times H, or A times H, H and H. And this comes from the equivalence relation that X is related to Y if X inverse Y is in H. Now, if I have a left coset, you might say, what about a right coset? So there is another equivalence relation defined as follows. X is related to Y if Y X inverse is in H. Not X inverse Y, but Y X inverse. If the group is abelian, these are the same. But if the group is not abelian, these are different. And the equivalence class is the right coset of H. So the right coset HA is everything in the form H times A for all H and H. That is, I take the elements of the subgroup H and I multiply them all now on the right by A. So this is a right coset. And Lagrange's theorem is also true for right cosets. So the number of right cosets of H in a finite group G is again the order of G divided by the order of H. So the index is the same whether you are looking at right cosets or left cosets. Now, in general, these are different. Let me see if I can think of a good example. Suppose I take G to be S3 and H, the subgroup generated by E, and let's say tau 1, where tau 1 is the transposition 2, 3. And I suppose I let sigma be the cycle 1, 2, 3. So I want to compute the left coset sigma H and the right coset H sigma. So what is sigma times tau 1? That's 1, 2, 3 preceded by tau 1, which is 2, 3. This sends 1 to 2, 2 to 3, and 3 back to 1, and 3 to itself. So sigma tau 1 is the transposition 1, 2, which I call tau 3. So sigma H, the left coset, it's sigma times the identity, sigma times tau 1. That's equal to sigma tau 3. That's the left coset. What about the right coset? Well, what is tau 1 sigma? That's 2, 3 preceded by 1, 2, 3. This sends 1 to 2, 2 goes to 3, so 1 ends up at 3. 3 goes back to 1, 2 goes to 3, goes to, so this is the transposition 1, 3, which is tau 2. So H sigma is E sigma tau 1 sigma. That's equal to the identity E and tau 2. So sigma H is sigma and tau 3. H sigma is sigma and tau 2. So in this example, sigma H is not equal to H sigma. So the left coset is not necessarily equal to the right coset. Right? It would be nice if that were true, but it's not always true. If it is true, though, it really is very nice. And we give such subgroups a name. We say that H is a normal subgroup of the group G if the left coset of H equals the right coset of H for all elements in the group. So if every right coset is the left coset, the subgroup is called normal. And in this one simple case, when normal subgroups are, where every subgroup is normal, if G is abelian, if G is an abelian group, and H is any subgroup, then the left coset, it's everything of the form A times H for H in H. But the group is abelian, so HAH is the same as HA, which is exactly the right coset. So in an abelian group, every subgroup is normal. And the important fact about normal subgroups, and I'm going to spend the next 2 or 3 or 4 lectures talking about, is the following thing. If H is a normal subgroup of G, then we can multiply cosets. And if H is normal, I don't have to say left coset or right coset, because every left coset is the corresponding right coset. I can just talk about a cosets. As follows, we define the product of AH times BH. So this is one left coset times another left coset. That's going to be equal to AB times H. And I claim that this is a well-defined multiplication. So I want to be, so this is going to define the product of 2 left cosets. And let's just assume for the moment that this multiplication is well defined. What are some properties of this multiplication? So recall G mod H is the set of all cosets, left or right in this case, AH, A and G. So this is the set of cosets of H and G with this multiplication. So if I take AH times BH and multiply that by CH, what do I get? This product is AB times H times CH. So this is AB times C times H. This is an element of the group. In the group, multiplication is associative. This is A times BC times H. It's this left coset, which is equal to AH times BCH, which is equal to AH times BH times CH. And this is the associative property. So coset multiplication is associative. Suppose I look at the coset EH, which is just H, right? This just means take everything in H multiplied by the identity. EH times AH is EA times H, which is AH. And AH times EH is AEH, which is AH. So EH or H is the identity in G mod H with respect to this multiplication. And if I take A inverse H times AH, A is in the group, A inverse is in the group. This is A inverse AH, which is EH, which is H. And A inverse times A inverse H is A inverse H, which is EH, which is H. So every coset has an inverse. The inverse of AH is A inverse H. Or we could write that as AH inverse is A inverse H. So therefore, G mod H is a group. If this definition of coset multiplication makes sense, the set of left cosets is a group. So from a group and a normal subgroup, I've constructed a new group called the quotient group or the factor group. It all depends on multiplication being well defined. So I want to show that if H is a normal subgroup, then coset multiplication is well defined. So suppose I have a coset AH, which is also A prime H for A prime in G, and BH is a B prime H for B and B prime in G. I must show that, actually, instead of calling it A and A prime, let me call it A1 and A2. It's my A1H equals A2H, B1H equals B2H. I want to show that A1B1H equals A2B2H, right? Because if I take A1H times B1H, that's A1B1H. If I take A2H and B2H, that's A2B2H. And these have to be equal for multiplication to be well defined. But A1B1H and A2B2H, that means this is the case if and only if A1B1 inverse A2B2 is an H. Right? Two cosets are the same. It means A1B1 is related to A2B2, which is the same as saying that B1 inverse A1 A2, B1 inverse A1 inverse A2 B2 has to be an H, because A1 B1 inverse is B1 inverse A1 inverse. And why is this true? Well, because H is normal, A1H equals HA1 equals A2H. So there are elements H1 and H2 in H such that H1 A1 equals A2 H2. This says that let's see. I'm trying to make this as easy as I can. So, sorry. So if A1 H equals HA1, this means that whenever I write A1 times H, that's equal to some H prime times A1, because A1H is in here and it has to be in here. So it's H prime A1 for some element there. So if and similarly for A2. So if I have B1 inverse, A1 inverse, A2, B2, this is B1 inverse, A1 inverse. Well, this is going to be a longer calculation than I want to do right now, since I only have a minute left. So this will be the first thing that I do on Wednesday. So what I just showed is, so here's the important takeaways from this lecture today. You have a subgroup of a group that defines an equivalence relation. The equivalence classes are the left cosets of the subgroup in the group. If the group G is finite, the number of left cosets is the order of G divided by the order of H. A subgroup is normal if every left coset equals the right coset. And in that case, there's a well-defined multiplication of cosets, and you can get a group called the quotient group. So this is really the core of algebra. And I will do this all from the very beginning on Wednesday, because the more times you do it, the better you understand it. Okay. Any questions before we stop? All right. So now we're doing serious algebra. Okay. Be back on Wednesday. Bye all.